Answers to assignment questions. Question 57. It's a roller coaster running down a slope. The kinetic energy and potential energy changes when the roller coaster is running on the rails. When it runs down the slope, its potential energy changes to kinetic energy. When it runs up, its kinetic energy converts back to potential energy, but the total energy remains the same. Question 58. Describe the potential and kinetic energy change of a ball when it bounces on the ground. At A, the point of release, it starts with high gravitational potential energy. As it falls from A to B, the gravitational potential energy changes to kinetic energy. In fact, the kinetic energy is highest just before the ball hits the ground. During the rebound at B, some energy is lost during collision, and so the ball rebounds with less kinetic energy, and so rises to a lower position at C. After rebound, when it moves upward, kinetic energy changes back to potential energy until it reaches point C here. Then the above process repeats as the ball falls again. Question 62. When ice at -10 degrees Celsius changes to ice again at 0 degrees Celsius, then there's no change in potential energy, but the kinetic energy increases. When ice changes to water at the same temperature, the potential energy increases, but kinetic energy remains unchanged. When water increases in temperature, then the potential energy does not change, but the kinetic energy increases. Lastly, water at 100 degrees Celsius changes to steam at 100 degrees Celsius. The temperature is the same, the kinetic energy should be the same, but the potential energy increases because it changes from liquid to vapor. Question 66. Is a glass of hot water. It cools down at room temperature. The temperature drops rather quickly at the beginning because the temperature is very high compared with the room temperature. Then the temperature drops more gradually, more gently when the temperature is closer to the room temperature. So we know that the heat loss at the beginning is larger than that after 20 minutes. Question 67. Is a glass of hot lemon tea with some ice cubes added. First, it forms a tea-ice mixture, which has a temperature of 0 degrees Celsius. The temperature remains at 0 degrees Celsius for some time, until finally all the ice are melted. Then the temperature begins to rise gradually back to room temperature. Question 68. If we use a immersion heater to heat water when the heat is turned off, the temperature will keep rising for a short time. Why? Because when we turn it off, the heater was still hotter than the water, so it takes time for the heater in water to reach thermal equilibrium, to reach the same temperature. Question 69. We are using a 30-watt immersion heater to heat water for 1 minute. The heat transfer, E, will be the power multiplied with the time in seconds. Question 70. The initial and final geometry readings are given. The amount of energy supplied should be the difference of the readings. Question 71. The energy used by a 3 kilowatt water heater in 15 minutes will be the power multiplied with the time in seconds. Question 72. The initial and final geometry readings are given again, but this time the final reading seems to be smaller. In fact, there is a hidden 1 in the front. Can it be a hidden 2? I don't think so. Question 73. We use the emission heater again. We can calculate the energy supplied by multiplying the power with the time, while the energy loss is 250 joules, so we may calculate the net energy gain. Question 74. The setup here is used to measure the energy to heat a cup of water using an immersion heater. And don't forget to label your diagram. Question 75. To measure the heat supply in the 3-minute heating, we should record the initial joule-meter reading. Then start the stopwatch at the time when the heater is turned on. After 3 minutes heating, we turn off the heater and record the final joule-meter reading. The energy supply is the difference of the two readings. Lastly, question 76. How can we measure the temperature rise then? We record the initial temperature before the heater is turned on. After the heater is turned off, then we record the highest temperature reached as the final temperature. The difference of the two temperatures is the temperature change. And now let's move on to the pre-lesson video of the next lesson. Chapter 3. Heat capacity and specific heat capacity. When we use an immersion heater to heat some water, then the more the energy supplied, there will be the higher the temperature rise. But how are Q and delta T related? The energy supply increases with the temperature rise. Or we may also say that the energy supply is directly proportional to the temperature rise. Or you may describe the relationship between them as. Let's find it out in this lesson. You will set up this experiment today to find out how the temperature rise, delta T, is related to the energy supplied, Q. In order to find the temperature rise, you must measure the initial temperature, T1, and also the final temperature, T2, which is the maximum temperature of water after the heater is turned off. And don't forget to keep stirring during heating to ensure the temperature is uniform inside the cup. You will heat it for 1 minute to find the temperature rise, and then 2 minutes to find the temperature rise, and again for 3 minutes and 4 minutes to find how the temperature rise and the amount of energy supplied are related. And to do so, you may mark the temperature after 60 seconds of heating, 120 seconds of heating, 180 seconds of heating, and so on, so that you may finish the heating in 5 minutes. After that, you plot a graph of temperature rise against the time of heating, and you will find a straight line graph that passes through the origin, which tells you that the temperature rise is directly proportional to the time of heating, which tells us that the temperature rise, delta T, is directly proportional to the energy supplied, Q. And so we write Q directly proportional to delta T and express it as an equation in the form Q equals C delta T, where C is called heat capacity, with a unit of joule per degrees Celsius. And what does that mean? For example, a small cup of water has a heat capacity of 250 joules per degrees Celsius, and it means that it absorbs 250 joules of energy in order to increase its temperature by 1 degree Celsius. And if it absorbs 500 joules of energy, then its temperature increases by 2 degrees Celsius. And of course, for a larger cup of water, then the heat capacity will be larger.